So in this lecture, we're talking about wave optics. We're getting started with chapter 27. So today, we review the various models of light and talk about diffraction and interference. So most of the time in this lecture will be on the double-slit interference. Okay, so chapter 33, wave optics. So we're jumping over many chapters. So those were primarily E&M chapters, which you did in Physics 2 in 162. Now, the type of phenomena we will discuss are interference, diffraction, and interferometry, so kind of an application of interference. And this chapter really directly builds on the chapter on superposition of waves, which we discussed before, chapter 17. So it's a very direct continuation of that material, and many of the results we find are just direct consequence of the superposition principle. All right, so let me take a look at the slides here. So we start with a preview of the material in this chapter. Yes, as I mentioned, there are various models of light. So light is quite mysterious. There are many phenomena that you can describe by a wave model, treating light as wave. So these are things like interference, diffraction, etc. There is a model of light which you can get in a particular limit of wave optics. So it's not really fundamental different, but in terms of the mathematics and modeling, it looks quite different, and that's called ray optics. So it's treating light as traveling along straight lines, and that's very useful in analyzing things like lenses and mirrors. So it's in the limit where kind of the interference phenomena are not that important and can be neglected. And then there's a fundamentally different picture of light, known as a photon model, which is fundamentally different, treats light as particles instead of waves. And it turns out that there are phenomena like the photoelectric effect where, light can cause electric currents which do not agree with the wave interpretation of light. So that's something that we learn about when we study quantum physics. It turns out all matter has this dual description. So in certain circumstances it appears it behaves like waves, and in certain circumstances it appears that it behaves like particles. And it's neither. It's whatever it is. It's matter described by the laws of quantum physics, which are quite counterintuitive and beyond the scope of this course. So the wave model is a classical model. It doesn't talk about the quantum nature of light, and it's very useful in understanding a wide range of phenomena, as we will see. So in this chapter, we'll talk about diffraction. So diffraction is a fundamental property of waves, the fact that they kind of spread out after passing through a small hole or going around the corner. So they don't move like particles, right? They're waves, and they spread in the medium. For light, there's no medium. they're electromagnetic waves that propagate in vacuum. But just the laws of electromagnetism kind of cause this propagation of the electromagnetic waves. And it turns out the smaller these holes are, for example, they can cause more spreading. Another thing we'll talk about is interference fringes. We talked a little bit about thin film interference before, right? When you had light reflected from two different surfaces, and we found, for example, conditions to create an anti-reflection coating. So we'll talk more about that. We also, in general, talked about interference phenomena in 2 and 3 dimensions and getting nodal lines, places of destructive interference and places of constructive interference. And of course, if you put a screen somewhere and detect the intensity of light, that can give rise to these dark spots and bright spots. So we'll explore the mathematics of interference a bit more. We'll talk about certain limits where the relationships simplify quite a bit, like when the screen is really far away, for example. I'm going to talk briefly about the diffraction grating. It's an array of closely spaced slits or grooves, and again it gives rise to some pattern of interference fringes, which is much more pronounced. As you can see, you get these narrow bright spots and wider dark spots. And then we'll talk about some applications. All right. So we looked at simulations like this in chapter 17. So a fundamental property of waves is that it kind of spreads out. Like when you have waves emerging from a point-like source, which is if you block light or waves kind of incident on some surface and just let them pass through small opening, that small opening for what's on the other side serves as a point source, and then one gets these kind of spherical wavefronts that can cause, disturbances over here and over here. So the waves can go around in some way, right? Even though these waves are coming this way, it's not that they just go through. If you had particles, right, you were shooting a bunch of particles. So the ones that hit the wall, hit this barrier, just get stuck or get reflected or bounce back, and the ones that are going straight kind of go through. But that's not the case with waves. Okay, so as a warm-up, this is a very similar exercise to the type of things we did in chapter 17. So take a look at this and decide what kind of interference you have at that black dot. Pause the video and come back when you're ready. Alright, so yeah, so the black dot, as you can see, is 1.5 wavelength from the top source, 1 to 2.5 wavelength from the bottom source. So the delta R is just lambda, and that's constructive interference. The phase difference is 2 pi. So yeah, so that's A is the correct answer because of this difference in distances of the two sources, which gives rise to a phase difference of 2 pi. Alright, so what we want to discuss now is something called the double-slit experiment, which is basically you shine light Let's say you have some laser beam and you shine it on two long, narrow openings. So basically the problem, as long as you're not close to these edges, you're somewhere in the middle, reduces to the interference of some cylindrical waves, right? You have these wave fronts that basically, like if you're far from these edges, like in the extreme case where the slits just go from -infinity to infinity, the wave fronts will be cylindrical. So if you look at one cross section here, we just see circles. And then because they both come from, so they act as two sources, right, in this two-dimensional cross section, and because both come from one laser, they're going to be in phase at the position of the slits. So it reduces the problems we've looked at before. We have two sources in phase and they emit circular wave fronts, and then at various points in space we're going to get either destructive or constructive interference. And then if you put a screen in front of it, well, where you have destructive interference, you have the nodal lines here. No light reaches there, those points of the screen, so you're going to get dark fringes. And where you have constructive interference, we get these bright fringes. So our goal here is to figure out the positions of these dark and bright fringes. So consider, let's say we have two sources, or these are the two slits which act as the two sources. And they are, let's say, some distance d apart. And then we put a screen, so let's say that's the middle point. And we put a screen here, which is a distance L from the two sources. We are interested in the limit of L much larger than D. Okay? So a lot of things simplify in that limit, and we're going to find very compact expressions. But first, let's try to remind ourselves of the kind of the general pattern. So let's say we're interested in finding places of maximum constructive interference on the screen. So let's say maximum constructive interference on the screen. So of all the places in space, we just focus on points on this vertical line over here. So clearly the central point is a point of maximum constructive interference, because R1 is going to be equal to R2, right? You have an equilateral triangle, so you just have 2 points a distance d apart, and you take their middle point and you go some distance, and then you draw 2 lines to those 2 points. So if this is equal to that, then they share this line. So these triangles are the same, and therefore R1 is going to be equal to R2. So central point, so let's say here we put some coordinate axis. Let's say here the central point on the screen, we call it y equals 0. So this is y. So that's y equals 0. And then, different points on the screen are labeled by this coordinate y. Okay. Now, so we found one point of maximum constructive interference, one bright spot on the screen. And then as we move away, well, the difference between R1 and R2, delta R changes, right? In this case, delta R is 0. So it's going to change continuously, right? As you, let's say, move this way, move up, for example. Again, let's draw this here. So 2 screens, we go somewhere here. So as you move your point along the screen, let's say this is R1, this is R2. R2 is getting, both of them, well, R2 becomes larger than R1, right? So delta R is increasing, and then when delta R first hits lambda over 2, you're going to get a dark spot, you're going to get destructive interference. Then when it hits lambda, you're going to get another bright fringe, another constructive interference. And yeah, and it keeps going. So we can do this kind of geometry in an exact way. We alluded to this before when we were talking about the curves describing nodal and antinodal lines. We talked about these hyperbolic curves, right, for fixed delta R. And we can do kind of the geometry and figure out this thing exactly. And then later we'll focus on the limit of L much larger than D and find simpler expressions. But for now, let's just do everything exactly here. So if the distance between the sources is D, I have D over 2 over here, I have another D over 2 over here. Okay, so what is R1? From here to here it's Y. So if you consider this triangle, from here to here I have Y minus D over 2. Therefore R1 becomes square root of Y minus D over 2 squared plus L squared. R2 similarly, so you draw this line parallel to this line, horizontal line, perpendicular to the screen and the line connecting the sources. And then from here to here, from here, where the point I'm interested in, the point where I want to find the interference, the type of interference or the phase difference. From here to here, I have Y plus D over 2, right? From here to here it's Y, from here to here it's D over 2. And then this is again L, so you use the Pythagorean theorem, you find Y plus D over 2 squared plus L squared. Okay. Then R2 minus R1 becomes this, right? L squared plus Y plus D over 2 squared minus L squared plus Y minus D over 2 squared. And yeah, so the first point where you have, let's say, the next bright fringe, so let's call that delta R. Well, first bright fringe, as we said, is a central point, is Y equal 0, and clearly that gives delta R equals 0. Next one must have Y equal lambda, right? The first one, the first non-zero delta R that gives you, must have delta R equal lambda, and Y we don't know what it is. So we don't know Y, but we know that delta R must be lambda to get constructive interference. And delta R is a function of Y, right? So you look at that function and solve for, you set this equal to lambda, then lambda is known, D is known, L is known. One can in principle find the exact value of Y. Now, what I want to do is consider the limit of L very large. So L is much larger than D and Y. Okay, so L much larger than d and y. Let's say assume we're interested in that limit. It's just we've put the screen really far compared to the distance between the sources, between the two slots, and we don't look too far from the central line compared to L. So L is really a large length scale in the problem that's larger than everything else. All right, so how can we approximate this? So what is the small parameter? Well, the ratio of y and d over L, they're going to be small dimensionless numbers. So I talked before about the general Taylor expansion theorem, right? Remember when we use, for example, the small angle approximation, we argue the sine of theta is close to theta if theta is small. It followed from f of, let's say, let's call it x, is f of 0 plus the first derivative at 0 times x plus the second derivative at 0 over 2 factorial times x squared, third derivative at 0 over 3 factorial x cubed, etc. Right? So we can truncate this at some point, and then, you know, where you truncate guarantees that you have the same value at x equals 0, the first derivative. So if you truncate here, say you keep the first two terms, you have the first value of the function at x equals 0 and the first derivative. If you truncate here, you match the function, its first derivative and its second derivative. And of course, if x is small, then higher powers of x get smaller and smaller. So it makes sense to truncate this at some order. And yeah, and we can find like the leading order if you just pick the first term that's not 0. Okay. So let me write delta R. I factor out an L, and then I get the square root of 1, right? L goes under the square root, becomes L squared, plus y plus d over 2 over L quantity squared. That's a small quantity, minus 1 plus y minus d over 2 over L quantity squared. So it seems the relevant function is the square root of 1 plus something small, right? So let's say f of x is square root of 1 plus x. Right? That whole thing is a small quantity. Y plus d over 2 over L quantity squared is a small quantity. So this I can write approximately as f of 0 plus x times f prime 0. What is f prime? F prime x, this is 1 plus x to the power 1/2, so its derivative becomes 1/2. 1 plus x to the power minus 1/2. Therefore, the first derivative at x equals 0 is just 1/2. So this becomes f of 0 is just 1, right? You put 0 in square root of 1 plus x, and then it's plus x over 2, approximately, right? This is the approximation here. So that's the leading contribution for small y over L and d over L. So then delta R in this limit approximately becomes L times 1 plus 1/2 y plus d over 2 over L quantity squared. That's our x. Then minus 1 plus 1/2 y minus d over 2 over L quantity squared. So this is, the ones cancel out. I get L over 2 over, let's say, L squared. And then you have y plus d over 2 squared minus y minus d over 2 squared. Okay, so then we can either expand these, right, and see what terms cancel out, or simplify it a different way. This is like something squared minus another thing squared, so reminder this identity here. A squared minus b squared is a minus b times a plus b. So that gives delta r is approximately 1 over 2L. The difference between these two things is the y's cancel out, d minus minus d over 2 minus d over 2 is d. And then their sum becomes 2y. So that's simplified significantly, right? So we found that delta r is in the limit of very large L approximately y times d over L. An extremely simple expression. Now the condition for constructive interference is delta r is equal to some integer times lambda, right? That's when you get constructive interference. And that means ym, let's say we call these ym corresponding to each integer, there's some distance, times d over L is m times lambda. So that means ym becomes m lambda L over d. So at least in this limit, we're going to get these bright spots. So let's say here is the y-axis. We're going to get these bright spots that are equally spaced, right, on both sides. And the distance between them is lambda L over d. There is an alternative, more geometric way of finding the same result, which we'll go over. So the thing we're going to discuss now is how this expression is derived in the book. So what we did was more of a calculus space, just using the Taylor expansion, approximating the exact result in that limit and just seeing everything pop out of the algebra. So we can also do this in a more geometric way. So the idea is, like, if L is really large, much larger than, say, the distance between the sources, the two slits, you take like you zoom out, you look at the setup, right, from a distance, you're not going to see D. It seems basically like if you're looking at some distance over here, it seems the lines connecting the two sources to that point are pretty much parallel. Right? If D is tiny, then the angle between them becomes really small. So, right, so take a triangle. And here you have a length D. Here, let's say you have a length L, right, in this direction. So in the limit of D much larger than L, this angle here goes to 0, right? You can treat the two lines as approximately parallel. Okay, and then let's say that point, these parallel lines form some angle theta. All right, now we can zoom in. So if you zoom in, now we look at the two slits. There's a spacing of D, and we see to reach that one point, the same point on the screen, approximately we have to move in the same direction by some angle theta. Okay? Now, so what is now the phase difference between these? Right? So if you look at some cross-section perpendicular to this direction of propagation, let's say, to reach that point, well, the bottom one travels a distance that's equal to d times sine theta more than the top one. Right? So if I draw a line perpendicular from the top source to this line at angle theta that comes out of the bottom source, in this triangle, d is the hypotenuse, and this length, this little length here, is opposite in angle theta. So let's call that delta r, and then delta r over d is going to be sine theta. Okay. So that means that delta r is d times sine of theta. And then we use the condition that delta r is m lambda for constructive interference. Clearly at m equals 0 we get the central point. And then furthermore, we make the approximation of a small angle. So again, if L is really large, the idea is that that distance on the screen, the y distance, is much smaller than L, so we can approximate sine theta by theta. We end up with theta m is let me do it slowly here in the notes. So that was one approach, geometric approach. So for large L, we're saying the lines connecting the sources to a point on the screen are almost parallel. So here we have source 1, source 2, distance d, and let's say these lines form some angle theta here. Okay, so then the wave coming from the bottom source travels a distance more here, delta r. So if this angle is theta, this angle is theta, and delta r over d is sine theta. So delta r is d sine theta. For constructive interference, we want delta r to be m lambda. That means d sine theta is m lambda. So let's call this theta m, right? For each m, we're going to get a theta. So sine theta m is m lambda over d. And now let's look at it from a distance. So these are the two sources here. Really, they look like a point. This is my theta m angle. And the idea is that ym is, again, much smaller than L. If L is really large, we can make that approximation. So sine theta m is approximately equal to theta m. This is the small angle approximation, which is really a Taylor expansion of the sine function and keeping the first term. All right, so that implies that theta m is m lambda over d. And now ym is L tangent of theta m. But again, in the small angle approximation, this is also approximately the same as tangent. So this is approximately L theta m, and that's m lambda L over d. So it's the same result we found before using this other approach, kind of the Taylor expansion of the exact result. All right. Okay, let's have a quick check here. So pause the video, try to figure out the correct answer here. All right, so this is a double slit interference pattern on a screen, and the point on the screen is marked with a dot. Is how much farther from the left slit than from the right slit. Okay. So yeah, so what is delta r, right? What is the difference between the distances from that point to the two slits? Well, here we have the central maximum, so for that delta r is 0. Then the next interference fringe, the bright fringe, has delta r equal lambda. This is in the middle of the next one, so delta r must be equal to 2 lambda. All right, again, another quick check, so think a little bit about this. Pause the video and we come back to it. Okay, so that's now the double slit interference pattern. And if the screen is moved farther away from slits, what will happen to the fringes? Yeah, so what do you think happens? So basically we found that the condition for getting fringes, at least in this approximation, was that we have these particular thetas, right? So if theta doesn't change, so theta corresponds, you see we had the expression theta m is m lambda over d, right? Just depends on, theta m just depends on the wavelength and the distance between sources. So let's say you're at some theta m, you're getting some bright fringe at some distance y here, and now if you move the screen over here, well, that distance gets bigger, right? So these correspond to the same m. We can also directly use our expression, right? Ym is ml lambda over d, so it's proportional to L. If you increase L for the same m, for the same fringe, we're going to get a larger y, right? So for all of them, all of these go farther from the center, right? They have a larger y, so therefore the distances between them should also get larger. It's pretty much like scaling, like blowing up this whole picture, right? Scaling it up, and all the distances increase. And in this limit of very large L, that's exactly proportional to L. So if you double the length, for example, the distances between fringes doubles. The distances double between the fringes. Okay, so here's an example. So we have a double slit interference pattern on a screen 1 meter behind two slits spaced 0.3 millimeters apart. 10 bright fringes span a distance of 1.7 centimeters. What is the wavelength of the light? Okay. So the model is, it's not always obvious which fringe is the central maximum. Okay, so, but we don't need to identify that. We can just think about the distance between fringes. So if you have, let's say, so example 33.1. So it says 10 bright fringes. You have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the bright fringes we see. And the problem says they span a distance of 1.7 centimeters. So from here to here, I have 1.7 centimeter. Okay, so then what is the spacing between these fringes, right? Remember, our ym is m lambda L over d, right? So it's just proportional to m. So if you look at two consecutive ones, so ym plus 1 minus ym, in this limit, it's just lambda L over d. So delta y is independent of m and is L lambda over d. So if you just figure out the spacing, we can use that expression. And the spacing is, well, if you have 10 fringes, you have how many intervals? You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So delta y is 1.7 over 9 centimeters. And that's equal to lambda L over d. So 1.7, let's say, times 10 to the minus 2, let's work with meters, over 9, is going to be lambda. L was 1 meter, so let's see, what was d? 0.3 millimeters, right? So d is 0.3 millimeters. So over 0.3 times 10 to the minus 3. And then this would give us the wavelength in meters. So lambda becomes 0.3 times 1.7 times 10 to the minus 5 over 9. That's in meters. Yeah. Let's look at the answer. See what it is numerically. Yeah. So delta y is 1.7 over 9, and then lambda is delta y times d over L. L was just 1 meter, d is 0.3 millimeters. So it turns out to be 5.7 times 10 to the minus 7 meters, or 570 times 10 to the minus 9 meters, which is 570 nanometers. Okay, so it's kind of interesting that this experiment has an application to metrology, right? You can use it to measure the wavelength of light by just measuring the distances between interference fringes. Okay, so here's another quick check. So think about it, pause the video, try to find the correct answer. All right, so this is the interference pattern from a double slit experiment. So the only thing we do is we change the light from red to green. Okay, so what happens to the bright fringes? So going from red to green, red has the lowest frequency and the largest wavelength. So when you go to green, you decrease the wavelength, right? You increase the frequency, you decrease the wavelength. So if I decrease the wavelength, what should happen? Remember, delta y was L lambda over D. So if I decrease lambda, L and D don't change, they're the same. So delta y should go down. The separation between fringes should go down and they get closer together. Here's another quick question, again checking the consequences of this expression that we derived. So pause the video, try to figure out the answer. Okay, so now we have these interference fringes, and what we do is we move the sources or the slits closer together. So what should happen to the fringes? Well, again, delta y is L lambda over D. So you make D smaller when you move the sources closer together. And because it's in the denominator for delta y should get larger, so they move farther apart. All right, I think that's a good place to stop, and we'll continue this discussion in the next lecture.